recording this, so if someone couldn't join or join late, you can hear it. I would like to introduce you Marco Esposito. I hope I pronounced it correctly. A postdoctoral researcher at the Italian National Institute for Nuclear Physics, to talk a little bit about FluTAS. Following to that, we'll have Filippo Spiga talk about quantum espresso. Marco, you can start.
Okay, thanks. I hope I can share. Yep, can you see?
Yeah.
Okay. So good morning, everybody. I would like to give you a brief overview of the code FluTAS, which stands for Fluid Transport Accelerated Solver, which I developed together with several people, which I will acknowledge at the end. I would like to just give you an introduction on how the code works, what are the equations behind it, what do we use it for, and ultimately also what can be done with this type of code. So just as a brief start, why do we develop this type of code? So this type of code is used for study in general multiphase flows, and multiphase flows can be almost anywhere in our everyday life. So for example, we do have it in the food industry, food production industry, or food treatment. For example, in the production of mayonnaise, you create an emulsion of oil and water, which you stir in order to produce the mayonnaise. And in order to simulate this type of flows, we can use our code. But we can also use it, for example, to study emulsions, such as the one which are created in the environment when we have an oil spilling in the maritime environment. It's very important in this case to actually understand how these large stains of oil breaks into droplets and how this droplet actually penetrates in the maritime environment and how they affect the fauna and the flora. Similarly, we can have industrial oil spills, not just from shipwrecks, but in general from any type of waste spill into any type of like sea or lake-like or river-like environment. But then there's also kind of different process that we can study with this type of code in general. So for example, like boiling process or bubble column reactors, everywhere where there is, for example, a bubble with interacting like surrounding water, that it's some kind of flow that we can approach, we can study. It's very useful to study also sprays, for example, like you can use sprays for, I don't know, like pharmaceutical devices when you're like spraying any type of drugs in your nostrils or around you and so on. You can also use it in propulsion. For example, in internal combustion engines, you have sprays that atomize your fuel, which is then burned to produce energy. You also have it in the aerospace sector. You have it almost everywhere. You can create pharmaceutical emulsions, which are less chaotic than the one we described before, for example, in the oil spilling, but it's very important also to understand what is the way in which flows interact when you mix them very slowly. And that is very important, for example, for drug companies or pharmaceutical companies. We can study how bubbles interact with the ocean, for example, or for example, how these tiny little droplets that we have on top of each wave is created. So all these type of things follows under a general umbrella of multiphase flows. And in some of them we have heat transfer, in some of them we have turbulence, in some of them we have different phenomena which are interacting. And ultimately what happens is that in these type of flows, it creates a very complex type of flow to study. And there is a need, to actually use very complex codes to simulate these type of flows. So far, the state of the art actually paints us a scenario where we have that in multiphase fluid dynamics, there is a substantial increasing in complexity, and especially in computing requirement. The reason is, first and foremost, the case that we're simulating becomes more and more complex. I don't know, many of you are familiar with, for example, Reynolds number, Prandtl number, Schmidt number, which are like dimensionless number, which are basically framing or characterizing our flow. But there is a reason for industrial and environmental application to actually push this number toward limits which are very difficult to simulate. And for example, when we have to have a lot of particles, a lot of droplets, a lot of bubbles or things like that, they require a lot of grid points per each diameter of this quantity. And when we have a lot of grid points, then ultimately it's quite difficult to simulate because we have huge simulations. The physics become more complex. We can, for example, have different type of physics interacting. So we have multiphase, we have compressibility effects, we have heat and mass transfer, phase changing, and so on. And right now there are a lot of codes which are basically geared towards simulation of these flows. Our code is not the only one. There's Bazel's Paris Simulator, NGA, and so on. There's many of them, but the problem is that some of these code are not general enough or flexible enough to accommodate many physical modules. And there's also another point which makes some of this code less appealing, and is the GPU acceleration. So as you all know, GPU has seen a huge growth in the last decades or so, or 2 decades, I would say. And they start rapidly to, let's say, replace the canonical CPU clusters. At least in Europe, we see a huge incremental increase in the GPU clusters. Roughly 30% of the top 500 right now is GPU accelerated nodes. And I don't know if these data are updated, as you can see they're from 2001, but 8 out of the 10 best clusters in the world right now are GPU. And the question is if we can adapt quickly, which for us is quite of a complicated question to pose, because as you probably know, when you create a GPU accelerated code, the code itself has to have a specific architecture, which has to be supported by the type of physics you simulate, but also by the type of application you want to simulate. And therefore, it's important to have this type of trade-off and have a code which is written in a way that can be easily expanded both for CPUs and GPUs. So in general, we want the code to be modular, as we said, because we want it to accommodate as many physical modules as we can, so that people can actually simulate very complex scenarios and very complex flows. And these has to be done with a relatively minimal effort. It has to run both on CPUs and GPUs, which is very important for the reason that I just showed you. It has to scaling well, both on CPUs and GPUs, which is a bit of a pain in a sense, because the good scaling in CPUs and GPUs is not usually given by the same characteristics of the code, but because we have the need to have efficient codes which runs on both type of architecture, the implementation algorithm has to be such that both scalings are well preserved, and also has to allow for a collaborative framework, which is also an important point. Like, nobody is able to do huge physics, develop very difficult or complex codes on his own. It comes from an international, usually collaborative effort, and therefore the code that you're using and the code that you're proposing to collaborate on has to be as flexible as possible and has to be easy for your collaborators to work on. So in this framework, we actually wrote the code FluTAS, which was a collaboration between KTH, NVIDIA, NTNU in Norway, OIST in Japan, University of Iceland, and right now there's several others which are participating in this, but those are like the regional part of this consortium. And let's say the rationale behind the code is quite simple. We wanted to simulate well multiphase flows with a transfer, at least at the current state of the code. And we want to be able to use an FFT direct solver, which is very fast for the type of simulations that we have to perform. We wanted to be able to run both on CPUs and GPUs, and to do that, we wanted to accelerate possibly through OpenACC, and some part of the code where OpenACC actually is not so easy to tune, we actually used CUDA. It has to be able to include different numerical methods, so it has to be able to account for different multiphysics part, but also for different methods to discretize your flow, and it has to be able to scale up to hundreds of GPUs. And we actually have been able to achieve this type of result. Right now, the code has been used on Prace and EuroHPC applications, So we are quite happy with the code performance so far. And let me just recall you the general governing equations. So in general, we have, well, let me just put everything out. In general, we have that the flow that we're simulating is the so-called incompressible flow, meaning that we have a divergence-free velocity field. For those of you who might be familiar with fluid dynamics, this is your Navier-Stokes equation, okay, where we have two important terms which we have to consider. One is the surface tension term, and the surface tension term is basically the interaction that we have at the flow interface. This flow interface is actually reconstructed at each time step. We're going to see how in a minute. And then we have the gravitational force when we have the so-called Boussinesq approximation. In order to compute the temperature at each grid point, we also use an heat balance equation, which is the third equation, this one. And finally, so in order to actually understand whether a grid point belongs to a certain phase, for example, either water or air in a bubble, in a flow with bubbles. So in this case, we have the advection of the scalar field H, which is an indicator function. And the advection, and through the manipulation of this field H, we're actually able to reconstruct the curvature and the normal at the interface. So in general, the code has a second-order incremental pressure projection method. And here are some of the references in case you're interested. The equations are discretized in space with central schemes and advanced with Adam Bashford or Runge Kutta. We usually, for this application, I think we're going to use Adam Bashford. The code use a FFT Poisson solver, which is based on a previous code that also people in NVIDIA poured to GPUs, which is called CANS. And let me give you a couple of more details on how the code actually needs to account for the reconstruction of the interface. So for example, we use a method which is called mthink, where we basically approximate the transition between the two flows, not like a steep function, like a Heaviside function, but we actually use a hyperbolic tangent. So through this hyperbolic tangent, we actually can tune the sharpness and we can tune the sharpness of this interface. And of course, the more we get towards the sharp hyperbolic tangent function, the more the transition between these two flows happens in a sharp way, which is actually the way in which it's supposed to happen in the real world. So this type of, why do we choose this type of reconstruction method? So you can imagine that when you have such a complex flow and H is actually a scalar field, which is all over your domain, you have to reconstruct the interface, right? In order to understand how the interface is actually interacting with the surrounding flow. But to do that is actually, if you want to have something which is just a geometrical approach, it means that these are going to be computational tasks that are going to be focused only on the interface cells. And if you have this type of focus for your code, it means that basically just some cells will work and some other cells will not, while through this type of algorithm, we have a more load balance way to analyze the behavior of the interface. And finally, through once we compute the distribution of the color function, we actually have that through a simple gradient operation base, we're actually able to compute the interface normal and the interface curvature, which is ultimately what we use to compute the surface tension forces. The interesting thing is that we can control thickness of the interface with this algorithm. We have exact volume and mass conservation, which is very, very important in these type of flows. And also, we have less local operation, as I said, compared to the usual volume of fluid method, which is generally a geometric volume of fluid. 2 words just on how the domain is discretized. So in CPU, we have pencil decomposition, meaning that we decompose. So you see, for example, here we have slabs. You can also imagine that in this case, we can actually split these slabs also in the other direction. So we can have pencils. But in GPUs, in order to speed up the code, we actually use slab decomposition. And slab is actually very useful for us because it allows us to reduce the number of transpose. Transpose, for those of you who are familiar with how an FFT is performed in 3 dimensions. So if you have an FFT in 3 dimensions, it means that you have to perform an FFT in each direction, but if not all the points are accessible at once, you have to perform all-to-all communication in this case, or transposes. And these are actually very expensive time-wise because GPUs have to communicate a huge amount of data. So the way in which we actually solve this issue partially is, instead of having 6 all-to-all, 3 for direct Fourier transform and 3 for inverse Fourier transform, we only have 2. And the way to do that is through pencil decomposition. And then we have Gauss elimination in the third direction so that we can actually solve our Poisson equation. Let me just give you a couple of examples of type of flows that you can simulate. So for example, I told you about mayonnaise, right? Mayonnaise is just an emulsion of oil and water, and the simulation that you're going to see is exactly that. So we put some droplets of, for example, oil into water, and we'll see how it evolves. And we force turbulence all around these droplets. So we have turbulence, which is mixing oil and water, and we can see that there is mixing between these two phases. It creates this type of emulsion, and it creates a lot of very tiny droplets and a lot of very large droplets, which are basically breaking down and then recoalesce on and on and on. So this is actually what happens when you steer emulsions with your fork, with your spoon, while you're doing it. And now, let me just show you the case that we're basically going to simulate in this. Well, it's a similar case to what we're going to simulate in this challenge. So basically, it's a relay-Benard convection. We have a cold plate at the top, hot plate at the bottom, and because the hot liquid at the bottom actually warms up, it starts going up, and when it goes up, it actually puts in motion this interface, which starts oscillating and adapting to the fact that it's pushed by the heat below, and actually push up from the below, push down from the cold vortex, which are formed in the top half of the simulation domain. So this is actually what we're going to simulate. And I'm pretty sure that you have a lot of information about the setup and the input files and so on in the wiki page that I think Ophir set up for you. But of course, I'm open for any type of question that you might have on this specific problem. Would like to acknowledge all my collaborators on this project, and the supervisor, who's Luca Brandt. Also, Filippo, who's going to speak next, had a huge impact on this project, so I would like to thank him especially. And I'm open for any type of question you guys may have. Hello?
Okay. This is Ophir again. How is it going? If you have any question, just go ahead and ask it. Open your mic.
It seems to have been very clear.
Everything is so clear. It's good.
Hi. So you spoke about interfaces. What exactly are those interfaces? Are they just surfaces we place into the fluid to actually see the fluid, or is it a physical phenomenon?
Yeah, it's a physical feature of your flow. So, for example, when you have you can imagine, of course, a droplet which is falling into air, for example, right? So, the point in which the fluid stops being air and starts being water, that's the interface. Okay, the interface is the two-dimensional, in 3D, of course, is the two-dimensional geometric feature which is separating the two phases of your flow in a multi-phase flow. Okay, so it's a plane, basically, two-dimensional geometrical feature which is separating these two phases. This is the interface in this case.
Okay, and the interface is computed by using this H function, the scalar function, which basically tells which fluid type is where, or?
Yeah, so we have, it's called a volume of fluid method. You can dig a a little bit in literature. I actually didn't told you guys, but this is a good chance to remind. We had a paper where we actually describe both the algorithms more in detail if you're interested, but there's also some computational details you might be interested in. So for all of you who are gonna work with this type of code, I'm warmly advise you to have a read to this paper, as there are going to be also some details that might be interesting for you for optimization. The paper is actually called the FluTAS, so it's very easy to find. But getting back to your question, yes, we basically advect the phase dispersed in the carrier phase. So for example, if we have bubbles in water, we advect the air phase, so to say. And then when we have the interface, there is a specific method, which is in this case called unthink, which is basically able to compute the mass flux, which goes from one phase to the other. So that's not really correct, but the way in which the interface moves. That is done through these advection, which is almost algebraic, and the flux is computed for this H function.
Okay, thank you.
You're welcome.
Hello, can you hear me?
Yep.
Can you also see us? Yeah, sort of, right?
Right.
Sorry. No, one question is about the input that we have to use.
Yeah.
So the general question is so are we allowed to change anything in the input? If yes, I mean, we know there are the parameters that are mapping the geometry to the MPI processes, for example. So can we change something there for the competition? So maybe it's a question half for you and half for the organizers.
I can answer if you want my share of the question. So in terms of the input, there's several of them. I guess the only one you should touch is DNS.in. I mean, you can play with everything, but the code might just crash and the results might not be.
No, yeah. I was referring to the DNS.in.
Right.
You're right.
Yes.
Yeah.
So if you're talking about DNS.in, I believe the last two lines, which are dims and actually you should just change. Yeah, you can just change dims. That's the only one you care about. That is basically telling you what is the geometry of the way in which you actually give a repetition of the processors, whether it is labs or pencils. So you have two numbers. When you're running on GPUs, usually you have slab decomposition, as we said. So the first number is 1, and the second number is the number of slices, the number of slabs you create. Okay, this is the way in which you run in GPU. Then, if you want to run it on CPU, you can play with all the numbers you want. You can also play with the way in which the pencils are decomposed, which is actually a preprocessor flag. So you have X pencils, Y pencils, and Z pencils in the makefile. You can play around with that and compile it differently and see, for example, whether the application speeds up or speeds down. From my perspective, you can play with all those parameters as much as you want. On GPU is a bit more strict if you have to profile it on GPUs or study it on GPUs, because there are certain configurations in which a code just won't work.
Yeah, thank you. And the first two lines, the one I taught, J taught, and K taught, and LX, LY, LZ, these are the geometry of the problem. So if we change it, we are basically changing the problem, right?
Yes. So just to give you an idea, let's say that the problem is it's a simple one, it's homogeneous and whatever. So if you keep the L size fixed and you actually change the number of points per direction, that means that you're basically increasing the resolution of the problem. So that you can try to do, for example, if you want to do weak scaling or things of this nature. But then keep in mind that if you do the same 100 time step that we decided to do, or you want to do whatever number of time steps that you want to do, in order to have the same physical time than the other case, you have to roughly multiplied by 2 the total number of time steps. Make sense?
Yeah.
Because
okay. Okay,
just
good.
you can also tell me if it doesn't make sense, and I will explain it again. But anyway.
no, it's fine. It's fine.
Okay, perfect.
Thank you.
Okay, guys. So thanks, Marco. And I would like to move to Filippo. If you have additional questions to Marco, please use our Slack channel, and we'll try to address it. And Filippo, go ahead.
Yes. Can you see my screen?
Yes.
Okay, so thank you very much. So sorry about last week. Life got in the way, so I was not 100%. So I'm here to present about Quantum Espresso as one of the application in this year challenge. This is not a new application, I mean that's happened in the past already. So I will present it again since compared to the past, some new bits have changed and been added. And then I'm gonna also explain a little bit about the two input and challenges that we have for you. So Quantum Espresso, so we spoke about CFD in the previous half an hour. Quantum Espresso is on the opposite side of the spectrum, I would say. This is material science. There's no really fluids, or at least not like in fluid dynamics. And in particular, we refer to Quantum Espresso not as a code, but a suite of code. So it's a big it's a big package with many source codes. And when you build it, it generates multiple binaries. And all of these codes are essentially a toolbox to do atomistic simulation. So understanding and simulating the matter at the atomistic scale, not understanding how that is structured, but also what kind of property from strength, superconductivity, all sort of things that come based on the state of matters. And Quantum Espresso is free. It's also very important in Europe. It's been supported by several European projects, including MAX, which is one of the European Centers of Excellence. And under this umbrella of this project, under this umbrella of this project in the past, let's say, 4 to 5 years, the development of the code, both in terms of CPU only, large scale, overall scaling, GPU acceleration, new physics, new parallelization strategies has been put forward. So now there's much a broader community of developers behind it, scattered all over the place. The fact that it's been an open source code compared to other codes in the same domain made Quantum Espresso suite very popular. And there are user and developer and contributors more or less all over the place. What is also interesting is that it's not just used by university, but is also used and customized by industries for a multitude of application. Application, as I mentioned, goes from the classic material science one, study metal alloys, study polymers, study batteries, study catalysis, electrochemistry. This is also applied kind of a lot in two major areas that are kind of important nowadays from the economic worldwide, which is green energy in general, materials, and energy materials for both storing, producing, and transporting electricity in this way, and also for obviously production of semiconductor, both at the atomistic level, more at the device level in terms of application. Who's using, as I said, is kind of a mix between industry and academia. Obviously, academia is the majority of the user that we have, but we are aware, the Quantum Espresso group is aware about industries that have been embracing open source software to do their own internal R&D. Sometimes they also contribute back, which is actually very good. So by being a suite of code, that means that when you build, and we go through the building process quickly, it's not difficult, but it has its own caveats, you generate a big number of binaries if you build all of them, okay? And there are some core binaries, PWscf, and then there are binaries that use part of this subset of the function and modules of this code to build more complex codes that are using large workflow. So today, it's very common that when people do material science research, they don't run just one big simulation and that's it. It's kind of true everywhere nowadays, but the material science has been for a long time where arrive to a scientific output or a scientific discovery was really about a workflow, which includes some basic type of calculation, for example, the ground state calculation with PW or the Ab-initio molecular dynamics with CP, and then on top of it, calculate extra property of the material, like the photon electron scattering, all sort of properties to basically say, oh, I like this material is resistant, I like this material is an isolator, and yeah, is an isolator. I like this material is a good conductor. I like this material is soluble in water, things like that. So some code are more popular than other, but they all start from, I will say, the ground state, the basic principles, which is PWscf or CP, and the one that I will mention today. We had the GPU porting of this code too. It's been something that's gone for quite a long time. It went to several iterations, several strategies. The code now in terms of coverage is not perfect. There's still part of the code that are on CPU only, but there are much more features that are extended to GPU. And what works or what doesn't is really, to be honest, input dependent. In terms of hierarchy, which is important if you want to do some analysis and if you want to do some more in-depth study of the code, which I think I mentioned is Fortran, but if I don't, it's better I say it, it's Fortran. So we have the general purpose layer, so the application, the tools in the toolbox. They have some common high-level libraries that interface linear algebra, FFTs, eigensolver, and things like that. And then there is some sort of, I would say, it's called an independent numerical API layer or library, but basically there are some more low-level library that abstract some operation, and those library call things like, Magma, LPAT, ScalaPack for eigensolver, they call BLAS for linear algebra, they call FFT of all various flavor type to compute fast Fourier transform. At this level is where the, let's say, accelerated library are plugged, while custom GPU may happen more or less all over the place, based on how the code is structured. But the bigger impact mostly come from the library. So plane wave cell consistency field, so the PWscf is the most famous code. 90% of the calculation that people do start with PWscf. It basically compute what is called the ground state using the constant equation, following the density functional theory framework. And there are some references for people who are curious here. There's some math. The calculation essentially plus FFTs, eigensolver, repeating a self-consistency loop that goes over and over again until essentially a threshold, a convergency test is reached, and that is where you reach your, your ground state. And then starting from there, more things can happen. The code is very capable because of the way it's parallelized, because of the way it's structured. And this is true for all the code in in Quantum Espresso, but obviously it's more obvious in PWscf because it's the most popular. He can handle atomistic system that goes from tens of atoms and few atomic species, like things that you can find in a battery in terms of lithium compound and things like that, to hundreds of atoms, so more complex structure with some periodicity, to very massive, systems in the order of thousands of atoms. The one on the bottom right is like it's a representation of what could be like a carbon nanotube with some probes, and you can, if you are in the order of tens of atoms, you can use one node, 10, 20, 100 core maximum. If you have in the order of 1,000 atoms, well, you need a supercomputer. In this case, you probably need few thousand cores, even more, or few hundred GPU or even more. So it's really varies. It varies a lot the type of size that the system can handle, and obviously based on the system, which means based on the number of atoms, the type of atom, the configuration of the cell, its periodicity, the profile of the application changes dramatically. It can be more blast bound, more FFT bound, more compute bound, and things like that. So there's not a single, there's not a single bottleneck. It's really about how the inputs look like. So in terms of parallelization, we'd apply to PW, but it apply to the whole QE because they share all the packages, they share the common module. There are multiple levels. They come to the way let's say the code is parallelized. You start with your MPI com world. There is a first initial trivial parallelization over so-called images. For the majority of the calculation, this is like a non-existent, like one, but it's there. Then you can distribute across what is called K point, which is very useful for spread across many nodes. The good thing about the K point parallelization is that each K point treats like a one cell that is replicated in the domain, and as a result, each K point calculation can progress almost independently, having its own FFT, its own Lagrange solver and BLAS, and then exchange only let's say rarely between them just to synchronize. And this is good. Obviously, you need to have a system with periodicity to exploit K-point parallelism. Give you an example. Let's assume that you want to simulate like a battery with a lithium compound. If you look inside the battery, you will imagine that your atoms are all regularly squeezed next to each other in all directions. So there is no point to have a cell that contains millions of these atoms if they are all very regular. Then you can cut a small cell with the minimum amount of symmetry and say, okay, this is my supercell, my minimum set. And then I imagine to replicate this cell in all over direction, and this is my K point. So can you imagine that to solve the problem over 1,000 millions, it's very complicated. Over small and then leverage some sort of replication, it's way more convenient. But if it's possible to use it, depend by the input case. Then there is this called band or G-vector parallelization. So when you actually split what are called the electronic states, this is like the basic one. Usually across one band group, you have all the plane wave coefficient, and you can have multiple band groups. At the current implementation, the band group is very, it's not super efficient in terms of memory. So often you will see that there is only one band group that contains all the MPIs that compute your calculation. And these are based on physics. So based on input, you can play with those. And sometimes you can, sometimes you cannot. It depends. You have K-point, you can use K-point parallelism. You have a lot of electronic bands, maybe electronic bands parallelism will work as well. Are you running a NEB calculation, which is a particular package, then you can leverage image parallelization. So it's really dependent. Beyond this point, everything else is more mechanical, I would say. Every subgroup, every small pool that contains one K point, or if there's only one K point, all K point, because there's only one, then you can do some basic operation inside that. You can do some FFTs, you can do some linear algebra, like a parallel distributed linear solver. Now, if you run on 100 MPI, you might decide that it's more efficient to run on 64 MPI only for your diagonalization. So there are parameters that allow you, when you run the application, I'll show you an example, to tune this low level fine grained parallelization strategies to get the most performance for those basic operations, the linear algebra and the FFT. In particular, the linear algebra, you can get if you have a number of MPI, you can get a subset of MPI that is a square, and that can be faster than just use all of them. It depends how big is the matrix. And for FFT, we have actually two strategies, which is one is by slab, that is very similar to the one that Marco described, where we have one direction plane, and then when you revert and you do an all-to-all, you get stick. Or we have also this called pencil, which is basically you start with stick, and you can basically transform in other stick by doing all-to-all, and then another set of stick by doing a second all-to-all. So slab is very convenient because you do less communication, or at least you do communicate more data. You shuffle around the same amount of data at the end of the day, but you do just one big MPI all-to-all call, and you just flip once your domain, but you are limited by the number of slab, meaning that if your domain, your cell has only 100 slab, because this is the dimension of the cell, you cannot scale over 1,000 MPI. It's just not There's more MPI than slab. It's not just doesn't work. There are tricks, but in principle, it doesn't work. So when you have this kind of scenario, you want to scale because it's a big calculation with a lot of atoms, so you have a lot of plane waves, so you need a lot of nodes anyway. There is the pencil decomposition that is allowed to basically use more. So if you imagine a slab of 100 on one side is 100 times 100 if it's a cube when you move from pencil. So just basically allow to scale much longer. And so play on these two is very important to figure out what performance is the best. So how to compile the code? So it's a Fortran code. You need a Fortran compiler, you need an MPI library. This is very simple. There's nothing to be scared about. Obviously, this is compared to FluTAS, for example, or other code, QE is heavily dependent by optimized math libraries. So whatever is your architecture system, pick the best optimized single node math library, BLAS, LAPAC, FFT, Intel MKL, 1MKL, ARM library, whatever it is. But also you need, actually this is not mandatory, it's a plus, but you can want to use some optimized multi-node math library. For example, Scalpa can help for the eigensolver. For this type of challenge, there's not really an IO focus. I mean, there is some IO, but it's not an IO, it's not an input that stresses the IO. But in principle, you could link HDF5 if IO is one of your concern. So we have a little bit of a more advanced IO subsystem. And in recent years, they decide to add a CMake, so you can build the code with autoconf or CMake is exactly the same thing. I would argue that probably CMake is the more documented one if you're looking for weird compiler flags, but it's also the one that if you get it wrong, it just drags you nuts. So autoconf and modify the file still works very well. So in terms of configuring the code, I do an example, the autoconf. So configure is very easy. You want to run in parallel, you want to run with OpenMP, so MPI plus OpenMP as a programming model is supported. You may or may not want to run with Scalapack. I believe in CPU only is the default. And then you do make call and you build all the binary you want. For the GPU, there is a little bit more to take care of. The Scalapack is not the default because we use a serial GPU accelerated eigensolver, but you need to specify that you want CUDA. CUDA means in this case GPU accelerated. You can or cannot enable OpenC. That does give you a little bit of a boost, especially for non-PWscf packages. But then you have to be very careful when you select which compute capability of your GPU is and which runtime do you want if you're picking up a runtime that is different than the default. To run is very simple. You can find a lot of tutorial, a lot of example how to run the code. There is an input file. You pass the input to the executable pw.x. If you want to play with the pool parallelism, you just specify a number of pool. If you want to play with pool and then the diagonalization, which are not, one does not require the other, they can use independently. You have to add NDAG. If you want to switch between slab and pencil, there is an extra, this is all a command line to recompile the code. This is called PD dot, basically true or false, that basically switched off pencil decomposition when it's true or slab decomposition, which is the default when it's false. So it's fairly easy to run the code. So what are the challenges? This is an example of the output for PW, but other packages are very similar. When you start, it gives you basic detail on the parallelization, how much nodes and blah, 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 blah. At the end, it gives you some clocks. So timing inside the code that are reliable. But they're not covering very fine-grained code. So if you want to study the performance or figure out what is the bottleneck, you probably need to do some work with a proper profiler. The figure of merit that we're going to use is essentially the wall time. In second, it's easy to convert in second. And obviously, the lower is better. That's kind of obvious. So what's the competition task? So we have two inputs. We want them to run. And we provide one that is very much of a standard, which is Aussurf 112. Aussurf 112 exists since probably 15 years. That allows you to help getting familiar with the code and get it running. The two input that we provide you, we've been a little bit cheeky this year because Quantum Espresso has been used already for several competition has been used so much all over the place that if you're looking for a benchmark, most likely you're going to find the result already on internet. So this year we decided to give you 2 inputs that are not actually PW. So we decided to give you 2 inputs that run on CP, one of the packages, which is used by less than 10% of the people using the code. So the way the parallelization works, the way the code runs, the way the the internal structure of the parallelism applies to CP as well. So everything I say so far, it's true, but it's a different code. So it's not PW.x, it's CP.x. And as a result, because it does different things, it behaves very different to what you will find in literature. And you can run this with CPU, and you can run this with GPU as well. During the in-person competition, we may have a secret input. It depends. We will decide later what to do. Depends how things goes in the next month or two. So how CP is different compared to PW? So PW takes an electronic system and calculate the ground state. Imagine like I have my atoms that vibrate, and at some point they reach a point where they're happy and calm. They reach my ground state. My electronic ground state is where they're happy, quiet, and they can do whatever they want to do. Ab-initio molecular dynamics is what the title say, is molecular dynamics. So you have atoms that move and change their configuration based on forces acting upon atoms, but it's done using an ab-initio approach. So the classic molecular dynamics they use with LAMPS, GROMACS, NEMD, blah, 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 they compute forces based on empirical potential. In this case, and they govern, they follow the so-called Newton equation of motion. In the ab-initio approach, the Newton's equation of motion are replaced with the Schrödinger equation, which is way more complicated to solve. This is a multi-body problem. You require approximation, require eigensolvers. It's more complicated. And what was simplified potential in the classic molecular dynamics, it replaced with something that is more close to the behavior of the atoms and the physics. So the idea of a molecular dynamic code, which is initial configuration, you do some statistics, you calculate new forces, you change the atom position, you go over and over again, applies to this ab-initio molecular dynamic approach. But the way you compute these steps, it becomes a little bit more complicated. And when you use the unfortunately this competition has to run in a time-bound fashion, but you used to have like a molecular dynamic, like I run half an hour and I see this molecule vibrating and dancing all over the place. With the ab-initio molecular dynamic, to get to that point, you probably have to run weeks because it's really very much time-consuming. And so to go a little bit more in detail, that might be able to help you to unlock what to do, how to do, and how to run the calculation. Recently, the Max European project ran a virtual school on advanced material molecular dynamics. Sandro Scandolo is one of the authors of the code at the very beginning, back in many years ago. So there is a recorded lecture and some tutorial, which is a very small, very small examples, like an equivalent of Ausur for CP, like with only 4 atoms, I believe, that allow you to get through a little bit and getting even more familiar with this code. As I said, it's behaved very much similar with other packages in the suite, but it's not the same thing. So if you have any previous experience with PW, well, this is going to be a little bit new, which I hope is also going to be fun. So what you can and cannot do from a competition point of view. So you can try whatever libraries and compiler you want. You can play with all the fine grain and coarse grain parallelization schema that I described before. You can play with all MPI, OpenMP, MPI plus OpenMP, GPU, non-GPU kind of mapping. You can oversubscribe, undersubscribe your compute node. It doesn't really matter. What you can't do, obviously, is modify the input file. There is a convergence criteria that dictate how many steps you're going to do. We need to do all of them. So everyone is at the same page. And I/O is not really massive in this type of what's called input files. But if you have a very slow file system, you feel a little bit of a penalty on it. So cutting completely the I/O, that's not allowed. I know that you have to submit the result in the script that you used to run. So because reproduce a calculation is never perfect, but the target is that whatever you're calculating and claim has to be no more than 5% different than what eventually I will be able to replicate on the competition system. And that's it. I create on the Slack on a dedicated sub-channel for Quantum Espresso purely because otherwise Slack explode on me and I don't see notification. Or eventually you can reach out by email and I'm happy to answer. And if the answer is relevant for a larger group, I will post it back on Slack, obviously, so everyone is the same page. If there are any questions, I'm happy to take it. Any question?
Hi, yes. With
Yeah.
regards to the K-point parallelization, I assume that's dependent on the input file, how many K-points there are.
Yeah.
Okay. And would you recommend altering the end pools for number of GPU accelerators, or is that trivial?
What do you mean by explain it to me a bit? What do you mean by explain a bit what you want to do?
So for example, splitting the number of pools. Say you have 4 GPU accelerators on your node, splitting the code into 4 pools, and then diagonalizing however you want among each of those. Is that going to give you a performance increase over, say, just one pool running on all 4?
Well, it depends. In principle, having one, so within one pool, you do a lot of MPI communication within one pool. Okay, because you have a lot of distributed FFT and essentially these are the all-to-all are the one that kills your MPI scaling. If you can reduce the pool to a minimum and map it to just one node, just one GPU, just something that is the smallest possible because it fits in memory, and it communicate less or it doesn't communicate at all, then obviously you're gonna get a boost in performance. But if it fits in memory, that is input specific. So until you try, you don't know. The code does tell you when you run, they tell you more or less because it's not perfect, but when it runs, it tells you how much memory is consuming, and you could probably try and do the math. So in the next iteration, you can reduce, increase, or adjust accordingly.
Thanks very much. Yeah, makes sense.
Any other question?
Yeah, I had one question about the output file. Can you scroll back to that slide, please?
Yeah.
So we have these 2 times, right? The CPU time and the wall time.
Yes.
Are they always going to be like, close? Are the values going to be, similar, or is it possible that we can have like, drastically different CPU time? Like, so if we assume like the wall time is like 2 minutes something, and and the CPU time is like 5 minutes, do we still accept 2 minutes 12 seconds as the output or as the submission answer?
So the CPU time, I honestly don't like too much the fact that you report the CPU time, but this is an heritage of the past, because interpreting this number required to understand. It tells you something, but it doesn't tell you the whole story. What matters to you is the wall time. Okay, this is end to end the time. The CPU time is the time that is spent running on CPUs. Give you an example. Let's assume that you are on a node, you run 1 MPI, and you run with 4 OpenMP, okay? Your wall, and you run for 1 second, your wall time is 1 second, because this is the time at the beginning to the end, running on a node for the entire application to start and finish, 1 second. But because you're running on 4 OpenMP, your CPU time will be 4 seconds. So 1 times 4. So the CPU time is the aggregated of all the time spent by one process across a multi-threaded execution, and is measured with a Unix syscall. Okay, so essentially the CPU time tells you if I'm going multi-threading, I'm actually using all the core all the time 100%. So you would expect this CPU time to be at least, so there are 2 scenarios. The CPU time is in between your wall time and this is the multiple of the wall time times the number of OpenMP thread that you're using. And that's okay if it stays in the between. Now, it just tell you a number because it's not pinpoint to any specific location, or it's not in the it's not easy to identify where the difference and the multi-threaded happen efficiently. Only through that number you can understand if it's efficient or not. You need to take a profile and do a proper work. As we put there back in the days, just to give an idea about is actually exploited or not. However, there can be a situation where your CPU time is lower than the wall time, which is weird because you say, how this can be possible? This is possible if for any reason you stall on I/O or you stall on MPI, which means that at some point the application sleep, put it that way, so it stays hanging, waiting for something in the system that is stuck. Can be the I/O, can be the MPI being extremely slow, and that's more a symptom that the system is something that is odd. So I will take that number with a pinch of salt. For a figure of metric, we need the wall time. This is the only one that matters.
Oh, yeah, thank you very much.
Any other question? Oh, by the way, this is the output of PW, so the output of CP would be slightly different. It will still have the wall time at the end, but maybe it's going to look slightly different on the left. But don't be scared. Any other question? So if there's no other question, oh yeah, go ahead.
Okay. Thank you, Filippo.
Yeah. So the slide, I sent the slide to Ophir. I really invite everyone to look at this lecture. It's a couple of hours. There's some physics and some explanation. It might cast a lot of light about how to actually use and run CP for the competition.
Okay, thank you, Filippo. I will upload the slides and the recording to the website. And again, if you have other questions, contact us on the Slack, use Filippo's Slack channel, or contact me. I'll try to address your questions as possible. And thank you all for joining. And see you on Wednesday for the POT 3D presentation. Okay. Thank you, everyone.
Is it Wednesday or Thursday?
Maybe Thursday.
Thursday.
Yes.
Thursday, right? You're correct.
Yeah.
Thursday
Okay.
for POT 3D presentation. Thank you, Panos.
Yep.
Bye, everyone.
See you. Bye bye.
Good luck. Bye bye.
Bye.